This is K8BYP on ground radials, the history of them, and why they should never be used on HF. In the early days of radio, the frequencies were extremely low, tens of kilohertz, VLF, LF. Today, AM broadcast is upwards of about 1.5 megahertz. But back in the day, it was impossible to have a quarter wave tall tower. The tower might be 2,000 feet tall. They were doing good to have a poor antenna tower at 150 feet. Receive antennas were universally long wires. I showed in a previous video how an end-fed long wire, which is half of that dipole, is not so much an antenna but a capacitive coupling against ground. And the old radio set didn't work well unless it was grounded. That's primarily picking up fields traveling in and along the ground. That's called ground wave propagation. It exists in AM broadcast. That's opposed to skywave. At higher frequencies, such as 80 meters on up, HF, we don't use ground wave, we use skywave. There's essentially no communications in HF along the ground. That's because the wavelengths are extremely short and the signals just tend to hop off and take off up in the sky. And that's what we want for distance propagation. The purpose of ground radials is to compensate for poor conductivity soil. In places that have good conductivity soil, they might not be neat or useful. It's possible to put up a HF vertical and ground the transmission line with a stake in the ground. It may work just fine, or at least it appears to. What isn't evident are the losses. In a dipole, there are 2 points for the transmission line to connect to, but the resistive value at the feed point depends on the height of that feed point above ground. In the end-fed vertical, there's only 1 point, so it is impossible to terminate a transmission line into the bottom of the vertical. There has to be another point, and that point is often, unfortunately, chosen to be ground or ground radials. So the radials, in the case of the vertical, can be a transmission line coupling. The ground is also a coupling for antenna near fields. The near fields are shown as the squiggly lines under the dipole, electric field lines from the antenna to ground, and from the vertical to ground. But here's our old friend, the proverbial CB ground plane antenna with 3 radials, but they're not really called ground radials. That antenna can be at 100 feet and still work. And there's no ground coupling on 27 megahertz at 100 feet. That proves the earth is not necessary. And it proves they're not ground radials. What they are is a coupling for the shield on the coax to be able to look into 2 points on the base of the antenna. And there are field lines between the antenna and the radials. One of the old physics books says that the earth is a lossy resistance at low frequencies, but a lossy dielectric at HF. It's an insulator, it's a dielectric, it has tremendous losses. Radials compensate for poor ground conductivity. So if the ground at HF is a dielectric, there is no ground conductivity. So it's utterly pointless to use radials. Because at HF, it's a dielectric, and in theory, dielectrics don't conduct. Radials can be used for VLF and LF, but should never be used for HF. Firstly, the antennas are small enough, short enough, that a vertical can be shunt fed. I have one. I recently worked in Europe with 1 watt CW. Nobody can tell me it needs radials. It's an absolute 1-to-1 match when it's not raining across most of the 20-meter band. No radials. There is a ground connection, but no radials. But the ground connection is through a short, rusted, painted 6-inch metal spike, and it is not about the antenna and not about radials. It's for some other reason. A good source for information on radials is the book Radio Antenna Engineering by Laporte. There's a section on radials, what they do. In no case are radials calculated at a quarter wavelength. Someone that says, I made my radials quarter wave long, have no idea what they're talking about. There's a formula for it. It's not 1/4 wavelength. If we consider that radials are generally pieces of wire, it's ludicrous to see how many dozens we can string out across a yard. Because consider the surface area of the ground that the vertical has to look at with its electrostatic lines, and then consider the surface area of all those wires. The surface area of the wires is trivial. The problem with radial losses that don't exist in dipoles is shown crudely by these drawings. There's on the left half of a dipole with field lines coupling to the ground. That's an electrostatic coupling. It can exist because of stationary charges. If they're stationary, there's no current and no losses. The E field lines moving between the wire and the ground don't necessarily induce current in the ground. But if we put a radial, especially buried under a vertical, according to radio antenna engineering, then there'll be losses, because that radial, with all those field lines, in theory from the top of the antenna down, are inducing currents in the radials. And in broadcast, they measure them. They measure the ground radial currents. That couples fields into the earth and causes huge losses. The losses are bad even at AM broadcast frequencies. They're worse at HF. So the theoretical 5.3 dB sub I directionality of a vertical compared to 2.3 for a dipole is somewhat or largely wasted by using ground radials, where that benefit can be picked back up by simply shunt feeding. And I just did a recent video on shunt feeding. There's a myth out there with dipoles that, based on this belief that all antennas must have grounding and ground radials, to automatically assume that since there's no ground radials on a dipole, then the transmission line has to be a counterpoise. And these are technical sounding terms just thrown together at random with no proof whatsoever. If that were the case, and the shield of the feed line did something, then it would not be possible to do what I just did with my 20-meter dipole. Instead of having the transmission line go straight down to ground, then over to the house, I lifted it up. Nothing changed. If that were a ground coupling or a ground radial, or actually what's called a counterpoise, the feed point would have changed. It made no difference whatsoever. And if that were the case, we couldn't use or would see a change in tuning of a vertical dipole with the transmission line coming straight out. A counterpoise is a radial wire. Radial just means geometry, but it is not a ground radial. The definition of counterpoise, according to, I think it's radio antenna engineering, is an elevated wire to increase the apparent capacity to ground. So it is not a ground radial so much. And basically what the counterpoise is, with an end fed, is simply making a screwed up folded dipole. It's very simple. Vertical has one wire, dipole has two. Put a ground radial on vertical, it just made an L antenna. So it's no longer just a vertical. So moral of the story is, ham radio antenna theories are from the 1920s. They have not advanced. They don't take into consideration modern electromagnetic principles, which are what govern here. And to understand this, we have to study electromagnetic theory and not just ham fantasies. And the difference is extreme improvements in antenna performance. KBYP out.